Hi everyone. Today what we're gonna be discussing is we jump right into it. How is a mask decoder in uh SAM model, which is segment anything model, is working? The encoder is a pretty simple image encoder. We have a simple prompt encoder which encodes the prompts that we're giving to the model, which can be anything ranging from other points. It can be some boxes. It can be grid of points. It can be also a text prompt if you're including a clip encoder. That being said, those things are passed together. So that prepares image embedding, which is coming here to the mask decoder, and the prompt encoder is embedding prompt tokens, which is uh, coming also to the mask decoder. Now, what happens is this mask decoder, when this was originally pre-trained, it produces some prompt tokens. Some output tokens when this is being trained, and those output tokens add recursively back to the model to give it some sense of where it should be, how those tokens should be intermixed with prompt tokens, and also act as a guiding mechanism for where to focus on the image when the mask is produced. So, output tokens act as a cursor themselves in addition uh, to the prompt tokens. Uh, but prompt tokens are like majorly saying that currently I'm trying to focus uh, at the inference time, I'm trying to focus on certain region of the image, but output tokens capture the overall semantics of what uh, the image can be, and based upon what image can be, these output tokens cross reference themselves and guide the model generally where to focus on and what type of structures uh, has the model been carrying. So these output tokens cross attend to themselves, so which is a self attention. So output tokens and prompt tokens are collectively called tokens, and they're passed to this self attention layer where they are doing self attention among themselves and understand the representation better of what each different token is trying to say or convey, and how are these correlated among themselves. Once the self attention is done, these tokens are passed to a token to image attention layer. In the terminology of the paper, token to image attention means tokens are the ones that are queries, and image is providing the keys when we are doing our attention mechanism, which is a key and core principle of how an attention is performed in the context of transformers. So tokens are the queries here, and images are the keys here. Uh, Token to image attention layer will basically make us understand what image portions or what image regions are of relevance to each token, and thus we will get an updated representation of the tokens after here. And we have a small mlp layer right after this, which makes a little bit more refined representations after your cross attention layer that was token to image attention. So we have a much finer representation of tokens here, which includes both the output tokens and the prompt tokens. This being said, that is again passed forward, that refined representation of tokens, to image to token attention layer. This fine representation will now tell the image, will now act as a value, act as a key to the image to token attention layer, where uh, it will tell the image where to focus on. So image, uh, so earlier in token to image attention, the prompt tokens, in addition to the output tokens, will have an understanding that this box or this point has relevance to which all parts of the image, right? But in the image to token attention layer, it's the opposite. It tells the image, different parts of the image, what, which is a query vector now, what different prompt types, different prompts, it relates itself to them. It relates the patch, the patch of the image relates itself to what part of the prompt that it relates the most, or how much percentages or how much ratios it relates itself to each of the prompt tokens, which is also coming with the refined representation. So it's able to focus much more nuancedly and much more in a more expressive manner. This happens twice. This happens twice. Uh, so now we have image representation here, right? And we have a token representation here. This can go on again. So this will again go pass through a self attention layer, then again token to image attention layer, then MLP, and that new image representation will be guided with this new prompt plus output token representations to have a much more refined understanding of both the image representations and the token representations. Once we have that, now the image representation, which was downsampled in the initial case. So if our initial image was 1024, it was downsampled by 4 times in on each size, on each axis, x and y. So it's upsampled by a 2x cross convolution, where it's upsampled again to the same size of the original image. So now the image representations are now the same size as what an original image was. Uh, while now we have now, but what we want at the output is a mask. So at the output, if we want a mask, then this image representation is again taken, and this new token representation is again taken, and we do a final token to image attention, which basically says that what part of the image should be, what parts of the image is of most relevance to each of the token present in my combined output plus from tokens vector. So it queries the image, what which parts are much more relevant to it itself. So at the end, what we get is an output token per mask, and this output token per mask and an IOU output token. So this is what I was talking about in the initial point, where I was mentioning that the output tokens is something which the model automatically produces. This output token is initially that was appended back initially as a recursive, as a recursive, in a recursive fashion, is actually now produced here, which is much more refined and capturing the semantics of the entire image, as well as it also understands what the prompt token was encoding. This output token per mask is now produced, and now this per mask output token is done it does a dot product with the image representation, which is actually a full size of the which is of the same full size representation of initial image. And that output token per mask, uh, after doing a small MLP, is done does a dot product per mask here, and it produces all the relevant number of output masks that we were concerned about. So in my case, I'm using this SAM model to uh, segment my brain image into 7 classes. So this output token has 7 classes. So I'm producing output token per 7 masks that I'm trying to produce. So there will be 7 such output tokens. Each of them will have a transpose of the output size that we are trying to produce here. So it's just a matrix multiplication here. So if you see, it's 256 cross 512 cross 5 cross 1024 cross 1024 uh and here, and this this will basically be, there will be 7 such vectors, and each of the vector is after the MLP would be having the size of uh I think it will be, so we want the same size of the mask of the same size as the image input, right? So it's doing a dot product per mask. It's not even a cross product, it's a dot product. So uh I think it has to be the same size because it's doing a just a dot product of each of the entries. So it's gonna be the same size as the image embedding, but upscaled version. And it produces the masks that we are concerned about. So that is the general architecture of what this SAM, how the SAM decoder works. On the other side, we have the IOU token, output token, which basically predicts how much um of the mask is of good quality. So intersection of union is produced, and it has an MLP layer again, and it produces IOU scores. Uh, the main purpose of this presentation was to understand how the masks are produced, and I think that was useful to you guys, and to able to understand how this SAM decoder is architectured and structured to produce the masks that we want. And it's kept very modular, yet still decently intuitive to help designers augment it according to their needs. If you have any questions, let me know, and thank you.